Look at the universe today and run the clock backward. The vast, sprawling cosmos shrinks down, closer and closer together, until everything that has ever existed is squashed into a space smaller than the head of a pin. To figure out exactly when that explosion happened, we need one crucial piece of information: the exact speed at which space is stretching out right now. We call this present-day speed the Hubble constant. The math here is incredibly elegant. If we measure how fast everything is flying apart today, we just hit rewind. We calculate the time it takes for matter to collapse back into a single point, and we have the exact age of the universe. The Hubble constant dictates the entire timeline of cosmic history. It tells us precisely how the universe grew from small to big. In theory, determining the age of the universe is a matter of simple arithmetic. In practice, our two most precise methods for calculating that number yield two different answers. For a long time, cosmologists thought they had the timeline perfectly solved. Their primary tool was a strange radio signal permeating space, called the cosmic microwave background, or CMB. It is the literal afterglow of the Big Bang, capturing the cosmos when it was just a 400,000-year-old fireball. To read this ancient light, the European Space Agency built the Planck satellite, equipped with ultra-sensitive radio receivers measuring tiny temperature shifts. This is the all-sky map Planck produced. It maps the exact temperature variations of that primordial fireball. The red blobs show where material was hottest and packed tightly together, revealing the dense blueprints where galaxies would eventually grow. By running these temperature variations through complex mathematical models, scientists determined how that baby universe grew into the one we see today. The math gave them a beautifully clean age, 13.82 billion years. The data from the cosmic microwave background is considered the absolute gold standard in cosmology. It is so robust that many researchers believed the true age of the universe was a closed case. But good science demands that a single measurement be verified by an entirely different technique. Testing that 13.82 billion-year timeline from another angle is exactly what broke the clock. The alternative to looking at ancient background radiation is to measure the present-day universe directly. You find objects in space, determine exactly how far away they are, and clock how fast they are moving away from Earth. We can't simply test this in our own galactic neighborhood. In the Milky Way, the gravitational pull of dense matter completely overpowers cosmic expansion. To see the universe stretching, we have to look out across massive, deep space distances. To measure distances that extreme, cosmologists use a step-by-step system called the distance ladder. You measure something close to establish a baseline, and then use that math to calculate the distance to the next object, building rung by rung. Rung 1 relies on parallax. Watching a nearby star from opposite sides of Earth's orbit reveals a visual shift, giving us the precise distance to stars called Cepheids. These Cepheids pulse at regular rates, revealing their exact intrinsic brightness. Knowing the true absolute brightness of these local pulsing stars gives cosmologists a benchmark. They finally have a reliable anchor point to start climbing the ladder out into the deepest parts of the cosmos. This benchmark is known as a standard candle. Think of a dark street lined with identical streetlights. Because you know every bulb emits the exact same amount of light, you can calculate the distance to the farthest lamps simply by measuring how faint they appear to your eye. Taking the mathematical baseline from our local Cepheid stars, astronomers climb to the second rung of the ladder. They use it to measure massive, extremely bright standard candles, like exploding supernovas in distant galaxies. Rung 3 takes us to the deepest edges of the visible cosmos. Out here, in giant elliptical galaxies, matter is spread so thin that gravity has no local effect, and the pure expansion of the universe takes over. By analyzing the light hitting our telescopes from these distant elliptical galaxies, astronomers check how red that light appears. The redder the light, the faster the galaxy is moving away from us. In March 2021, a team of scientists measured the light from 63 of these giant elliptical galaxies to calculate the expansion rate. Running the clock backward from this specific data, they found the universe to be 13.3 billion years old. The verification test worked flawlessly, but the answer contradicted the gold standard. We now have two highly precise measurements from two completely distinct methods. The ancient cosmic background gives us 13.82 billion years, while the modern distance ladder gives us 13.3 billion. That is a difference of roughly 6%. To anyone balancing a checkbook or estimating a commute, a 6% margin of error sounds perfectly acceptable. But on a cosmic scale, that 6% gap represents hundreds of millions of years of celestial history. That is enough time for entire galaxies to form, live, and die, a massive chunk of time that either exists or it doesn't. 50 years ago, our telescopes and instruments were rough enough that scientists would have celebrated a 6% margin of error. Being that close would have been a major victory. Today, with multiple independent techniques and hypersensitive satellites, that discrepancy is mathematically impossible to ignore. The numbers are simply too precise for this to be a calculation mistake. This anomaly suggests that a crucial piece of the cosmic puzzle is missing. Reconciling the two ages would mean uncovering a physical process that has, until now, remained hidden.